Welcome, dear students, for the next lesson. In this lesson, we are going to see a molecule as a rigid rotator. So, we are going to see here a diatomic molecule considered to be a rigid rotator. In this lesson, we will learn some mathematical manipulations and find out the energy of a rigid rotator, that is diatomic molecule. Just look at the picture here. We have two atoms, that is M1 and M2. They are connected by a bond. They are allowed to rotate when it gets energy, fixing a point at C as axis of rotation. So, keeping a point at C, this axis, this rigid rotator can rotate. The distance between these two atoms, M1 and M2, is R, and the distance between M1 and C, the point of axis of rotation, is R1, and from C to M2 it is R2. So from the equivalence law, we can say M1 and R1 is equal to M2 R2, and we can also say this R is combination of two different lengths, R1 plus R2 is equal to R. From these two equations, we can find out what is R1 and R2. Like that, R1 is equal to M2 divided by M1 plus M2 into R, and again R2 is equal to M1 divided by M1 divided by M1 plus M2 into R. Now, the moment of inertia of a molecule about the axis of rotation can be given as, we have studied this word molecule, the moment of inertia I is equal to mr square in the lower classes. The same way, we can at the point of axis of rotation, we can say I is equal to m1 r1 square plus m2 r2 square. So from this equation, by substituting the above values of r1 r2, we can have I is equal to m1 m2 divided by m1 plus m2 into r square, where m1 m2 divided by m1 plus m2 is called the reduced mass, can be symbolized as mu of the molecule. So as a result, you have I is equal to mu r square. Thus, the diatomic molecule is equivalent to a single point mass. That's the conclusion that we are making here. Diatomic molecule which is rotating at a point C, keeping it as axis. So it is considered as a single point mass at a fixed distance r from the axis of rotation. Such a system is called rigid rotator. So you know, from this Schrodinger equation, for a rigid rotator, del square psi plus 8 pi square mu divided by h square, that's s square, it's not h2, E psi is equal to 0. So solving this equation here, the potential energy is 0 because it is fixed, r is equal to, r doesn't change, so the v is 0, so we don't here put v. And if we can solve this equation by variation method, by solving this equation by variation method, we can have derivations of like this. And finally, we have equation 8 pi square IE divided by h square is equal to j into j plus 1, where j is simply the rotational quantum number. So the energy can be derived as by mathematics, h square divided by 8 pi square I into j into j plus 1 is here, j into j plus 1. This expression where h is the Planck's constant and I is the moment of inertia, and here instead of I we can put IB or IC since both are equal in the linear molecule. The quantity j, which takes the integral value from 0 upwards, is called rotational quantity. So here we are going to discuss now the spectrum of this rigid rotator. So you know the energy has been derived from solving this Schrodinger equation. H square divided by 8 pi square I we have solved into j plus 1 that we have seen on the earlier slide. And when you divide this energy by hc, it becomes wave number. So Ej divided by h is equal to h divided by that h goes off. H square, instead of h square we write h 8 pi square hc IC into j plus 1, that is written in the centimeter minus 1 because the wave number is calculated in centimeter minus 1. It is inverse of the wavelength, where c is the velocity of light and is expressed as centimeter minus 1. And j value can take from 0 to infinity, from 0, 1, 2, 3, 4, 5, so on and so forth. So we can write the above equation as E is equal to B into j plus 1, where B is the rotational constant. B takes the value h divided by 8 pi square hc centimeter minus 1. So from the above equation, when you put epsilon, that is the wave number, is equal to B into j plus 1, the centimeter minus 1. When you put 0, the wave number becomes 0, so you put here wave number, and the value also becomes 0. So at point j is equal to 0, there is no rotational spectrum. At that point it becomes 0, so we don't get any rotational spectrum. And when you put j is equal to 1, the rotational energy is E1 becomes 2b, and we have a little higher and goes on increasing. When you put j is equal to 1, 2, 3, 4, 5, like that, we have the values as 2b, 6b, 12b, and 20b, and 30b. It goes on increasing. One can here find out that there is a increase in the band gap goes on increasing as the value, the me value or the wave number value goes on increasing. So at one point, as it goes on increasing, at one point there is a possibility of disruption. The bond between the two atoms can get broken as the value goes on increasing. So in the normal temperature, it is not possible that it get broken, but when in a higher temperature, as it rotates, there is a possibility of bond break. If we imagine the molecule to be in the ground state in which no rotation occurs, as we said, j is equal to 0, so it becomes no rotation. To raise a molecule to j is equal to 1 state, you have you just put here. So in the ladder of the band, there is a possibility of transition from one energy level to the next neighboring level. There is no possibility of transition from 0 to 2, or from 2 to 4, or from 4 to 6. There is a possibility that the transition in rotational spectrum can occur just one energy level to the next neighboring energy level. That we call it as selection rule. And those transitions from 0 to 2, from 2 to 4, from 4 to 6, all these transitions are forbidden. So in this rotation spectroscopy, del J, the selection rule is plus or minus 1. That is, the plus 1 is absorption and minus 1 it is emission. So with that, we know now what is rotational spectroscopy and how the rigid rotator is considered as a single point mass, and we also studied the spectrum of a rigid rotator, and we have derived what is the value of the mu, that is the mu value of the rotation spectra. From that we have seen how from one level to the next level the band gap goes on increasing, and we have seen also the selection rule. Basing on the selection rule, the rotational spectra is obtained.